All right, we may continue. So the three-dimensional of this is very similar to actually the two-dimensional one. You're going to see that the book describes it exactly the same way we do. So here is this lemma is what we have observed visually for an edge to block a certain pulling direction. We have seen that it has to be at least 90 degrees. I mean, it has to be a bit less than 90 degrees. So now here, if you look at the lemma, the polyhedron P can be removed from its mold by a translation in direction D. So this direction D, it was this x1 vector in the two-dimensional case. In the three-dimensional case, this direction D vector will be represented as a three-dimensional vector in which we fix the z coordinate to 1 and xy will be something arbitrary. If and only if D makes an angle of at least 90 degrees with the outward normal of all ordinary facets of P. So this is it says that it has to make more than 90 degrees, but this is with the normal of its faces. So it's actually the normal of a face was the opposite direction of the normal of the mold. Therefore, for example, if this is the normal of the mold, this is the normal of the face, so it has to make more than 90 degrees. So we first make this observation. If you're thinking about the faces or the edges of your polygon, the pulling direction, if you go back to this GIMP, the pulling direction, as you can see, we have it here. If this is the normal, the blue one is the normal of the face, or in this case, this is the normal of this edge. From V6 to V1, this is our edge, okay? We may call it edge 6. If you look at this edge 6, its normal is this direction. And the pulling direction, therefore, could either be at least 90 degrees. So in order for the pulling direction be valid, it has to be more than 90 degrees, all right? So the pulling direction should be in the opposite direction of this edge. It has to be at least 90 degrees with the edge of the polygon or the face of the polyhedron. So this is the first thing we have is this lemma, and after this lemma, this gives us constraints that look like this. So here in the book, as you can see, this n is the normal of a certain face. If we take the dot product of that normal of the face with the vector dx, dy, and 1, as you see, the coefficient of when you multiply this nz, as you can see, dz is set to 1. Therefore, the only two things that are here unknown are these two things. These nx, ny, and nz will be given to us by the polyhedron's faces. And this, since the angle should be more than 90 degrees with the polyhedron's faces, being more than 90 degree becomes equal to less than or equal to 0. So we include equality because if you just pull in the parallel direction of the face, if this is your face normal, you can pull exactly 90 degrees to that. It means that you're just sliding the mold across that face. It's also possible. So 0 is included. Okay, less than or equal to it has to make greater than or equal to 90 degrees. It means that the dot product should be less than or equal to 0. All right, so if you look at this, so we will have such kind of a constraint for every one of the faces of the polyhedron. In the one dimension, this was a one-dimensional problem in the 2D case. If in our case we were looking at the constraints like these, what we had were intervals on the one-dimensional x-axis. X is greater than 3, x is less than 10. They were half lines. In the three-dimensional problem that is in the book, well, what we have is each of these constraints that are like this. So for example, we will have constraints that are like this. 2x minus 3x minus 2y plus 5 is less than or equal to 0. Okay? If you look at this constraint, this linear constraint, this actually describes a line. All right? So this is the equality case when 2x minus 3x minus 2y plus 5 equals 0 actually describes a line. All right. So this describes a line, and less than 0 indicates a certain half plane to the certain side of this thing. So less than or equal to 0 means that we're interested in this half space. So here, half plane actually. Okay, so these are half, this is the whole plane. In 2D, we have this constraint describing a half plane. So this describes a closed half plane. Well, I say closed because the boundary, the edge, this line is also included. Okay, therefore the half plane is a closed half plane in which its boundary is also included. If this was less than, strictly less than 0, this will be the line will not be included in the half plane that we are interested in. In that case, it will be an open half plane. All right, so but we have a closed half plane, and each of these constraints are half planes like this. And when we have multiple constraints, 1, 2, 3, for all the faces of our polyhedron, it will actually be the problem we will try to solve is intersection of these half planes. Okay, so that's where the book is going to get us next. So here, as you can see, the feasible regions, I mean the half spaces, are shaded here with dark gray color. Not all of it is shaded. The side that is the feasible region of a half plane is shown with this dark color. As you can see, when we intersect those, this becomes the intersection of those half planes. Then that becomes our feasible region. Sometimes the intersection again may be an empty set. In that case, we will just say that it's not possible to manufacture a mold for this. The solution is infeasible. All right, so this is, we will be, the next part is given such constraints like we have here on GIMP. All right, given constraints that are linear, this becomes a 2D linear program with the objective function. If you also have an objective function, say for example, minimize x plus y. This may be an objective function. Minimize x plus y, or maximize, whatever you want. Minimize, maximize. So it's just going to be arbitrary. As I said, this is not relevant to our problem at all. It's just going to, actually it will be relevant in the sense that when we will just, if you want to just return one value out of all, instead of, if you don't want to return all the possible feasible pulling directions, but instead return one of the feasible solutions, we need a mechanism to select. This may also be considered in mathematical terms as a regularization factor. So we want to, for example, if this triangle is the feasible region, if you're minimizing or in this direction, we may select one of the corners of this triangle as our pulling direction when we optimize an objective function like this. Actually, this will be important for us to have an objective function because the randomized expected linear time algorithm is going to make use of the fact that we are maintaining a single solution at every step. We will not be looking at the entire set of feasible solutions, but every step we will just maintain a single feasible solution, and we will update it as needed as we process each of these constraints iteratively. So it's going to be an incremental algorithm. Incremental in the sense that, so we are going to have an incremental algorithm in which we are going to start with the first constraint and process these constraints as we go along. And after all the constraints are processed, we are going to have a correct solution. Okay, and the incremental algorithm, its basic invariant of the algorithm will be if the first n of the constraints are processed, the current solution is a valid solution for the first n constraints. All right, so this is, it will be incremental in the sense that we will incrementally process these constraints. It will be randomized in the sense that what we will do is we are going to randomly shuffle, create a permutation of these constraints so that we will start processing these constraints at an arbitrary order, arbitrary permutation in some random order that will make the algorithm randomized. Okay, so its randomization will come from the fact that we will process these in random order. You may ask, why does it matter if all of them are going to be processed? Does the order matter that much that we want to shuffle them? Actually, it matters. If somebody, if this was a question in some kind of competition, programming competition, for example, if somebody gives you the input in such a way that the input order is really bad, it may actually give a result in an O(n) square worst case behavior. Okay. For example, you may be familiar with this worst case behavior from sorting algorithms. For certain cases, for example, for certain algorithms, certain input cases, for example, if the numbers are already sorted or if they are reverse sorted, it may be very bad for quicksort. So you may think about things like that in this case as well. I mean, if somebody gives you a very badly ordered set of constraints, you may be resulting in a worst case complexity of O(n) square. But with randomized algorithms, we are going to make sure that this never happens, because whoever is giving you this constraints, you're free. After you have all of the constraints, you're free to start processing. After you have all the constraints, you can just shuffle them. You can just put them in some random order and you then run your algorithm. This makes the algorithm randomized. Okay, and that part is not difficult actually. Creating a randomized algorithm, just shuffling it in the first step is not difficult at all. What makes randomized algorithms difficult in the context of algorithm design and analysis is their analysis of running time. So if you have a random algorithm like this, how can you talk about expected running time? What is the expected value of the running time? So that's requires some statistics or some kind of a different more difficult analysis than at first seems. But if you can figure this out, if you can solve this complexity analysis problem for this randomized case, if you can provide the expected value of the running time of this algorithm, it will tell you a lot. We will say that, so we will talk about the expected running time for this problem. We will see in linear time expected running time algorithm. Right? This is not the same as average running time. Okay, so it's expected running time actually requires some kind of probabilistic analysis, and we are going to see that. All right, so let's continue. So here, the final result we are going to get at the end actually is written as a theorem at the beginning. So if we have a polyhedron with n facets in n square expected time, so it will be O(n) square expected time, because we will try to solve for one of those 2D LP problems. We will have an expected running time of linear O(n), and we will have to do this for all of the faces of the polygon one by one, because we don't know which face of the polygon could be the top face beforehand. So all the polygons, all the faces of the polygon or the polyhedra are tried one by one, and therefore that makes in total O(n) times expected O(n) and expected O(n) square time algorithm. So it can be decided whether the polyhedron can be castable in O(n) square time. If it's castable, the algorithm also results in a mold and a valid direction for removing the polygon from the mold. It can be computed the same amount of time. So section 4.2, I'm going to skip over this quickly because I'm more interested in this incremental randomized algorithm. This half plane intersection, I'm going to still go over it, but not go over the details here. The half plane intersection, our problem is half plane intersection. These are our constraints, all right? So each of the faces gives us a constraint like this, and our goal is to intersect all of them. So here is an divide and conquer algorithm for that. So by the way, another thing is when we're intersecting this half planes, the result will always be a convex region. When you intersect half planes, the result is always a convex region. But sometimes the result may be infeasible in the case. So these are the different cases when you intersect different half planes. These are the different cases you may have. The simplest cases, you have a bounded region like this, a convex polygon. It may be a convex polygon. In 2, 3, it may be unbounded. Okay, the intersection may be an unbounded region. It may be unbounded in both directions. It may be unbounded in one direction, but it may be an unbounded region. It may be a single point. The feasible region may be a single point, or it may be an empty set. So the intersection here is empty. The triangle here is not the intersection. This one is pointing this way. This one is pointing up. This one is pointing down. So the feasible regions are these shaded regions. So therefore, their intersection is an empty set. Okay, so these are the 5 different cases we may have when we try to intersect half planes. So here is the algorithm. The divide and conquer algorithm looks very much like the merge sort algorithm. So we are given a set of half planes in the plane, and the output will be the convex polygonal region, which may potentially be empty or unbounded. If the cardinality of the half space is equal to 1, which means that if the half plane just contains one half plane, so actually this is the input is a set. So H is not a single half plane. It's a set of half planes. If it contains only one half plane, then if the set contains one of them, we just return the unique half plane H as the feasible region. Okay, so this is actually our base case. When we have only one thing, we just return it. Okay, so just like merge sort, if you're trying to sort a bunch of numbers, if you just have one number, it's already sorted, so you return it. So this is exactly like that base case of merge sort algorithm. The other part is, as you can see, recursive. We divide our half planes into 2 equal size sets, H1 and H2. We first intersect the half planes in the first set, and then we intersect the half planes in the second set, which gives us 2 convex regions. C1 and C2 are 2 convex regions, possibly unbounded. All right, but we know that they are 2 convex regions. And if we have a way, if we can do the step 6, intersect convex regions. So that's something else. It's not the intersection of n half planes. It means that you're given 2 convex regions. Imagine you have 2 convex polygons. How can you find the intersection of these 2 convex polygons? That's actually a reduced problem. Okay, we have 2 convex polygons and we try to intersect them and find their intersection, and this could be done in linear time actually. So this part can be done in linear time. It's just like the merge step of merge sort. If you're given 2 sorted lists, okay, if 2 lists are sorted, you can merge them in linear time easily. So this becomes like the merge step of merge sort. Therefore, we get ourselves the recurrence relation is Tn is equal to 2 Tn over 2 plus On. This gives us an n log n algorithm. So let me write it here. So if you look at this intersect half planes, okay, so the recurrence relation of the running time, the computational complexity is basically I have 2 Tn over 2 because each of those new sets contain half of the plane, and I call this function recursively 2 times. So this is the recurrence relation for the time complexity. And also I claim that I can find the intersection of 2 convex regions in linear time. So if this is the case, we get ourselves at n log n. So in other words, Tn is equal to O n log n. So this is the n log n algorithm, which actually finds the intersection of half planes. So if you use this to solve your 2D linear programming formulation of your problem, at the end you are going to have n squared log n time algorithm in total, right? If you use this section 4.2's algorithm to solve the 2D LP problem in n log n time, you're going to solve it for all the faces, for all n faces or facets, which means the faces of the polyhedra. Okay, for all n facets, if you run this O(n) log n algorithm, it will result in an O(n) squared log n algorithm for worst case, O(n) squared log n worst case algorithm. Now we are going to convert this. So this is the part where we actually find the entire region of intersection of these half planes. Now we will see something else. Instead of, do we really need to find the entire region? Do we really need to find this entire region? Because our goal is to just figure out whether it's castable or not. And if it's castable, just manufacture one of those molds. So in other words, either vertices of these or any point on this region, feasible region, will do for me, all right? So I don't need the entire half planes. I mean, if in your problem, you need the entire feasible region to see how dynamic a mold can be, if you want to do it, or how dynamic the pulling direction can be, you may need to use this n log n algorithm. But if your goal is just to figure out that is the feasible region not an empty set? Is there at least a point in the feasible region? Because that's what our goal is, right? We want to figure out whether a shape is castable or not. Therefore, instead of maintaining the entire intersection of these half planes, you're going to maintain a single point at each iteration. This is the feasible point, all right? So that's the leap. That's the difference in terms of idea. That's the difference we're going to take in order to turn this n log n algorithm into an expected O(n) time algorithm. So, and this part here, the algorithm to find the convex intersection of two convex regions is described here. Okay, but I'm going to skip that one. You're not, so it's just a number of cases that are considered. You're not responsible for intersection of two convex regions. Okay, so I'm skipping this part. Yeah, here is the recurrence relation. The intersection of the convex regions, convex polygonal regions in the plane can be computed in linear time. I'm skipping this part. Now, here is the part that I'm interested in, because that's the linear programming is our focus on this chapter. And what we are going to do is try to solve this problem. So this is a linear problem in D dimension. This is a D-dimensional linear program. In general, we have linear constraints on the variables. As you can see, they have different coefficients. And we have an optimization function which tries to maximize a certain linear combination of these unknown variables. So in the two-dimensional case, we're just going to have a problem in which we are solving things like 2x plus 3y is less than 5 and things like that. Okay, now what we are going to do, actually, let me describe before going into what the book talks about. I'm going to tell you the algorithm. It's very simple, actually. You're going to understand from here easily. Now, we will first start. The algorithm is like this. As I said, we are going to maintain the current feasible point. Let's call this, let me use the same terminology as the book. Let's call it CI. Yeah, I think actually I think it's going to be VI. Let me see. And it's called VI. All right. Yeah. Okay. Now, since we are maintaining a single point, we call it VI. Okay, so VI indicate the current feasible point if after the first I constraints are processed. Okay, so we start with V0. In order for this algorithm to work, what we first do is we first bound the entire. For example, you may have some minimum x or maximum x that you will already allow. All right, so this minimum x, maximum x, we need to first start with a triangle. In other words, we add ourselves new constraints saying that x is less than this max x is less than, and x is greater than or equal to min x, and two other things. Y is less than or equal to minimum y, and y is greater than or equal, less than or equal to maximum y, and y is greater than or equal to some minimum y. Okay, so this min, max, these four values need to be also input to us in this version of the problem. So we need to, if we are going to find a solution, in our case, we first bound our entire feasible region with some minimum maximum values. So let's see in the book what it talks about these M1, yeah, these lines. So here are they. Let me show you the initial. Yeah, these are the two new constraints, the big M. Okay, it's possible to, in section 4.5, it's also talks about how we can actually solve for unbounded cases as well. I'm going to skip that part. So because the important part here is that to understand this incremental randomized solution, we have this M given to us as input, some large number. We don't want our solution xy values to be greater than or less than these values, all right, greater than m or less than minus m. So this is given. So in many practical applications of linear programming, a bound is actually a natural restriction. Okay, so this is the here is this is the paragraph where it talks about this bound, and the reason we need this bound is that in order to maintain such a vertex at every iteration, the optimum vertex at every iteration, our solution should be bounded. The unbounded cases of this linear program, it will be difficult to maintain such an optimal vertex. So what we first do is, actually this max x, min y, they're all, this is m minus m in the book, and in terms of so the coordinate of this location is mm, this location is minus mm. So we first bound our entire potential region. Instead of being between minus infinity and plus infinity, we put it between minus m and m. Now, depending on if our objective function is maximize xy, what we do is, if you try to maximize xy, if you look at the coefficients or dot xy, x plus y, if you maximize x plus y, this gives you two coefficients, c1 and c2, to be equal to 1 and 1. So the 1, 1 vector is this vector, right? So whatever the coefficients of x and y are, it tells you the optimization direction. So it tells you, for example, if I ask you maximize x and y, and there are no constraints. The only constraints are these four constraints. What would x and y be? It will be m and m, right? So it will be actually, it's, if you look at this rectangle, it's the extreme point in this direction. So if you go over in this direction, in this rectangle, the extreme point in this direction is m, m, and that maximizes this x plus y. So at every step of the algorithm, we are going to find an extreme point in a certain, in a given direction. The direction is always, it doesn't change. The optimization function is always the same, but we will we will maintain this extreme point. So in other words, we do it like this. We first start V0 is equal to mm. We start with this condition of the algorithm. Now, at every iteration, when we consider new constraints, we are going to consider the remaining constraints one by one in some arbitrary order. What will happen is that we will take a look at that constraint. Okay, actually let me try to draw something like this. Okay, in which we are still here doing, and the extreme point here is here. So if the constraint is, this is the half plane, this is the first constraint saying that minus 3x minus y plus 3 is greater than 3, for example, if we have something like this, okay, and if this defines this line, and this is the region, if this is the feasible region, what we need to do is, as you can see, V0 is no longer, V0 actually is outside this feasible region of this new half space, okay? This half space has a feasible line and it has an unfeasible line. How can we figure out whether this is infeasible or unfeasible? We just plug in V0 into this constraint. Instead of this x and y, we can just plug in m and m here. If you take a look at this, minus 3m plus 5 is not going to be greater than 3. So this actually does not satisfy the constraint. So just by plugging the current maximum, we can figure out whether the after processing this constraint, whether V0 is inside the feasible region or not. So this is what we are going to do for every constraint. If the current optimum Vi is included, is a member of the feasible half space of that current constraint, don't do anything. The feasible region, the current extreme point will still be extreme point in that intersection. If not, if V0, as in this case, for example, as you see in constraint 1, V0 is actually outside the feasible region of this half space, what do we need to do? We need to update V0 to be some point. We need to update it basically. And this updated point is by no chance actually, it's always going to be, that extreme point is always going to be a point on this line. It's never going to be inside it, all right? The extreme point is always going to be a point on the line defined by the constraints. So the algorithm therefore is this simple. It's just saying that for every constraint, okay, for every constraint, for all of them, for every constraint, if Vi, let's call it, for every constraint, let's call it Vi. The constraint is Ci, okay? If Vi minus 1, if the previous case, is an element of this Ci, if the Vi minus 1, the optimum point, the extreme point that we have figured out up to now, is already an element of the half space indicated by constraint I, do nothing, because it will, or actually not do nothing, we have to do this. Vi is the same as Vi minus 1. Do nothing means that Vi is the same as Vi minus 1. Else, if that's not the case, we need to update Vi, or find Vi in such a way that update Vi minus 1, Vi is going to be the new optimum point, will be some point along this line. And how do we find V1 here? We find V1 actually by solving a one-dimensional version of the problem. If you look at these, the previous 4 constraints, all of them intersect with this line, right? For example, this one intersects here, the other one, the bottom one intersects it somewhere here, the top, this one, the left one intersects it here, okay? And this one, the top, this is the left top. These are the intersection points, Okay, the intersection points of the previous constraints, and the other one is actually outside somewhere here, with our new constraint. Each of these intersection points, as you can see, the right boundary, what does the right boundary says? The right boundary says it's the feasible region is to the left. If you look at on this line, the intersection point of this, it says to the left, it's actually any point on the line towards the left of this region is feasible for the right boundary. For the left boundary, this is the intersection with the left boundary, any part to its left is feasible. So as you can see, the interval is now reduced to this one, and the top boundary says it's actually this is the feasible region of the top boundary. It reduces the interval to this region. Now this becomes the feasible interval. Actually, as you can see, this is really the feasible interval here on this line, and we are going to choose one point on this line. We do it by using this direction. In this direction, this vertex is the, I drove this vector in such a way that it's not directly orthogonal, which it's towards a little bit this side. So this vertex becomes the feasible vertex along this line. So actually, you could have chosen any point on this line if you do not consider the objective function. But according to the objective function, you're allowed to, after you find this interval, feasible interval, you either select its left side or right side that will maximize or minimize your objective function. Okay, so or if your objective function is directly orthogonal to the feasible interval on the current constraint, then you can pick any one of the edges. You can pick this one, any one of the endpoints. You can pick this one or this one. That will still be valid. All right. So in order to do the update, as you can see, we had to spend OI time or some linear time, because what we did was we solved a one-dimensional linear problem in order to find the new point on CI. CI is the constraint at step I. In order to find the feasible point on it, what we did was we intersected all the previous constraints, which was this right, bottom, top. So right, bottom, top, left, right. We intersected all of them one by one with this one. So it actually takes linear time to do that. So if you look at this for loop, if we enter the else statement at each time, it will take ON squared time. All right? Because for each of the constraints, there are n such constraints. If you spend OI time for each of the constraints, it will end up with an ON squared algorithm. So when we need to modify, if there's another, for example, if there's another constraint which is like this, and it's below, and I need to update it like this. If I need to update it like, if you need to update the objective, the vertex, the extreme vertex at every iteration, this results in an ON squared algorithm. So actually, it's worse than the n log n half plane intersection algorithm, the divide and conquer one. So it's not a very good algorithm if you just look at it this way. But here is the thing. What is the probability that you enter the else part? Because if you do not enter the else part, look at this. If vi minus 1 is already an element of the current half space, you just do something that is in constant time, in O1 time. Vi is equal to vi minus 1. Its cost is very little, just constant time. So now the problem is, if you need to analyze this algorithm. So how frequent we go into the if part of this for loop, how frequent we go to the else part. And it turns out that as the algorithm progresses, okay, this is like a reverse analysis. It's also called reverse analysis. Like, think about the last point vi, okay? Imagine you have, actually you can take a look at this one. Let me take a look at look at this one. This is the solution. Imagine you have looked at all the constraints one by one. You have computed everything. You have computed all the ones, the last one. And then the feasible region, the solution turns out to be this vertex here. Okay? You have n such constraints. If assuming that no two constraints, these lines, not at most two lines intersect at a point. Imagine two of them, only their intersection points are just unique. The intersection points are determined by two of those constraints. What is the probability that the actual solution is a point of the last two constraint lines? I mean, you have n of them, right? You have n constraints. Each of them define a line, and the last one, what is the probability that the actual solution is defined by these two? The probability is just 2 over n, right? Because there are two of those, and there are in total n of them. So the probability that this point is a member of them, is defined by them, is 2 over n, or close to 1 over n. So this basically tells that the probability that you're going to go into this else part of the algorithm is actually going to be that probability is going to be equal to 1 over I, which tells you that as the algorithm progresses, as the number of iterations increases, if you come to the 500 iteration, the probability that you will go into the else part, you will need to update the current objective, current extreme vertex, is very low, 1 over 500, and it will increase every time you proceed with the algorithm. So in the first iterations of the algorithm, you update the extreme point frequently, but as the algorithm progresses, the probability to go into the else part decreases and decreases and decreases. So if you compute this, the probability of going into I is 1 over I. You sum over all I from 1 to n. If you do this, at the end it turns out to be linear. All right, so if the probability to execute this OI part of the else part drops and drops every iteration as the iterations enlarge, as the iterations get larger, if this probability decreases, you get yourself the expected running time of the algorithm will be linear. So that's basically the randomized algorithm that we have. Since it's, as I said, it's probabilistic, somebody may give you a certain arrangement of lines, half planes in certain order, such that you need to update it at every iterations. For example, if I give you half places which are parallel to each other like this, okay, and the feasible region is always below, and I give you the order in this direction. This is the half plane, this is the second half plane, third half plane. You may need to update it at every iteration. So this is the bad ordering. But what the algorithm suggests is that if you just permute, if you just shuffle these half planes initially, meaning that nobody will be able to, I mean, the probability that that particular ordering of that particular permutation of the half spaces to come up as a result of shuffling is extremely low. Out of all m factorial shufflings, the ones that give you the worst cases are going to be a very particular ordering of those things, and an arbitrary permutation will not have this worst case behavior. All right, so therefore the expected complexity will be linear, and you can actually try this by implementing a version of this algorithm for a different problem. I will also talk about that, but that's basically the algorithm. That's, if you look at this pseudocode, yeah, this one, if you look at this lemma 4.5, for a constraint between 1 and n, for a certain constraint, let vi be the extreme point that satisfy all of the constraints up to ci. Then we have this lemma states that if the previous extreme point is an element of the half space indicated by this constraint ci, then we don't need to do anything. The new extreme point will be exactly equal to the previous extreme point if it's already inside. So just think about it like that. If the previous half plane already contains the intersecting part, the intersection doesn't change, all right, because that's the intersection. If the intersection is included here, that will remain as intersection. But if the intersection is not included or partially included, if that point is not included, then we need to update intersection. So this is the case 2 of this lemma. If the previous extreme point is not in the half plane indicated by this constraint, then either it's an empty set. So there are two cases. Maybe we may have an infeasible solution too. Okay, either we have an infeasible solution, or if we have a feasible solution, the new extreme point will be on the line that is indicated, represented by this constraint ci, on the line where Li is the line bounding this half space. And this is the proof illustrates the cases with different half planes, and at the end we get ourselves this bounded linear 2D bounded linear program. This is not randomized because it doesn't shuffle it first. The randomized version, which is described in the next section, just shuffles, permutes the given planes by using a linear time shuffling algorithm. So if you look at this, this is the algorithm. Let's V0 be the corner of C0. Let that corner MM that I showed you in the figure. And let these H1 to HM be the half planes of the constraint set. And starting from I1 to N, what we do is, if the previous extreme point is inside that half plane, we just update Vi to be the previous one. Otherwise, we find a new point Vi on the line. So this is the part where we solve the one-dimensional linear program, which we have seen at the first hour actually, by just maintaining a minimum x and maximum x, but this time parameterize. Our x-axis becomes the line itself. The Li is like our x-axis, and we either go above or below based on the intersection points with the other half planes lines, Li's, Li minus 1, Li minus 2. Then we look at the intersection of L1 with Li, L2 with Li, all the way up to L minus 1 with Li, and based on that intersection point, we define an interval on Li that is feasible. Okay, if the interval turns out to be an empty set, we report that the linear program is infeasible. Otherwise, we update it to one of the endpoints of that interval. And here is the analysis of the algorithm, and that's actually the expected part. We can see that the worst case is ON square, and the worst case can be obtained in this figure if we are given the half lines in this order. If this is H1, and if this is H2, and then H3, H4, H5 is given to us like this in this direction, all n minus 2 of them, we may need to update the extreme point at every iteration, and that gives us the worst case behavior. But in the randomized case, we'll see the probability that that happens is going to be lower and lower at every iteration. And here is the randomized version of that algorithm. I don't know why they put another pseudocode for this, because the only difference from the previous algorithm is that step 2. At step 2, whatever input that is given to us, we just compute a random permutation of that by shuffling the input. And shuffling the input could be obtained with this very simple algorithm. So given an array of elements, how can you randomly shuffle those array of elements? Here's how you can do it, such that every permutation is equally likely. So you can do it in a number of ways, but some of the ways that you choose may be biased towards certain permutations. If you want any permutation to be equally likely, this is the algorithm that you need to use. For k is from n down to 2, we just generate a random number between 1 and k. So we first, for example, generate a random number between 1 and n. Then we generate a random number between 1 and n minus 1. Then 1 and n minus 2. And what we do is, after we generate that random number, we swap the last element with that randomly chosen element. All right? So, and that last element is decreasing at every step. So the last element at first is n, then it becomes n minus 1, n minus 2, n minus 3, like this. So when the last element is n minus 3, we generate a random number between 1 and n minus 3. If it turns out to be somewhere here, we swap them. All right, so this algorithm, as you can see, is just one for loop. It goes over the entire array one time. So it's linear, its computational complexity is linear, and it generates a random permutation of an array of elements. So we can use this to generate a random permutation of our half planes or constraints, and then by using that, here is the analysis that we do. The expected value that this else part is going to be executed turns out to be 2 over I. So what is the probability that this vertex here is going to be bounded by 2 specific half planes that appear at the end? That becomes 2 over I, and if you do this summation, turns out to be linear. So the expected running time of your algorithm becomes linear. All right. So if you do the randomization, you will always observe a very fast algorithm. This is what it says. And actually, I think I gave the last section of this as a programming assignment so that the students try and see it indeed is really fast. Actually faster than the n log n algorithm, which is we may have a worst case n log n algorithm. This expected time linear algorithm really works faster than the n log n algorithm most of the cases. All right, so I'm going to skip section 4.5. Actually, we may maybe have another break because I also want to talk about one final problem about randomized algorithm. It's a really nice problem, and I will finish with that. Or maybe let me just spend 10 more minutes. I will just be able to finish the rest of the lecture in 10 minutes. So let's not have a break and extend this ending of the lecture. So I'm skipping 4.5. You're not responsible from 4.5 and also 4.6. 4.5 and 4.6 is skipped in this chapter. And I just want to talk about this 4.7, the smallest enclosing disk problem. And I'm going to refer to our slides for that. We also have a set of slides. You can take a look at it later if you want, but it's just a repetition of what the book already says. But in a nice pictorial manner. So yeah, I'm going to be using the slides for this problem. Randomized incremental algorithm for smallest enclosing disk. So the problem is this. We are given a set of points on the plane, and our goal is to find the smallest disk. This means it's a circle in which the area is also included. Okay, so it's if you just say circle, a circle indicates the boundary of this. When you say disk, the interior of the circle is also included. So find the smallest circle, you may also say, or smallest disk, which contains all of the points. That's the problem. And you may think about this problem coming up in robotics, in which you may want to place a robotic arm in such a way that where should I play it? What should be the center so that I would be able to access all of them? Not one of them will be far away. So I want the smallest radius circle as possible. And the output of this is unique. That's one lemma that we are not going to prove now. But a unique circle exists actually that encloses all. When the number of points is more than 3, probably there will be a unique circle. When you have 2 points, for example, there will be infinitely many circles. There are infinitely many, but the smallest of them is still unique, right? If you have just 2 points, the smallest enclosing disk is the one in which the line that connects these 2 points passes through the center. So the midpoint, if you have just 2 points, so what I want to say is, let me also try to draw this. If you just have 2 points, the smallest disk, so if these are the 2 points, the smallest disk that encloses these 2 points are the ones in which the midpoint of this line segment is the center of the circle. There are many other circles that pass through these points. For example, this one. There may be large circles that pass. There are infinitely many circles that pass through these 2 points, but the smallest one will be this. Okay, there's also, if you are given 3 points, okay, we have covered this in the first week of class. There's a unique circle that passed through 3 points. Okay, so in that case, that will be the minimum enclosing circle. Now, the algorithm is really simple, actually. It starts like this. It's an incremental algorithm. Given a set of points like this, first select 2 points randomly and start with them. Okay, start with a circle that have these 2 points. So if you have all the points from P1 to Pn, by using P1 and P2, draw the smallest enclosing circle that passed through them. Then for I 3 to n, this is what we do. If Pi is already an element of the current circle, let's call the current circle Ci. So we actually, when we put P1 and P2, we actually name C2 is equal to the unique circle in which the center is the midpoint of P1 P2 line. Okay, if this is the P1 P2 line, we just use its midpoint as the circle center, and that becomes our C2, the current minimum circle. So if the next point Pi is already in the current circle, what do? We don't do anything. Actually, we do this. It's Ci minus 1. We say Ci is equal to Ci minus 1. So the minimum enclosing circle doesn't change. If the minimum enclosing circle that encapsulates the first I minus 1 points also includes the ith point. So if the ith point happens to be inside that circle, do I need to update that circle? No. The minimum circle that encloses the next point will still be the same if Pi is inside this previous circle. Else, so this else part is really interesting. If Pi is not inside that circle, for example, if we include this one, okay, just consider these 3 points. This is outside. Now, this part is really interesting. It says that if this point is outside the current minimum circle, then the minimum circle at Ci should be a circle that should have this Pi at its boundary. Okay, so this sentence is really important. So in order to, just like when we were updating Vi, the Vi, if it was not included in the half space of the current constraint, what we were doing that is that the next extreme point should be on the line bounding that half plane. It's very similar to that. If Pi is outside the current circle, the minimum circle has to have Pi on its surface. Okay. Now, what I do at this point is find minimum circle such that it includes Pi on it. So it will have Pi and the rest of the points. By using Pi on it, and look at the rest of points, which is, when I say rest of points, points that are processed up to now. All right. And the second algorithm, this find min, in which Pi is, in which one point is known to be on the circle. So now this is a different function. We try to find a circle in which we already know one of the points has to be on it. Okay, now we run the algorithm this time, now including pi and one of the points here on it, all right, as the initial circle. So the initial circle changes as this because it finds it's going to update the CI. CI is going to be the new minimum circle, which includes pi on its surface. So we now start with pi n1 by using pi n1 as your initial circle. Okay, pi and p1 as your initial circle. You now say, okay, if and the second algorithm is almost similar to this one. If the you again have a for loop there. If the next point is inside the current minimum, you update it like this. If it's not inside, then now we have something interesting. Both of the points, both pi and pj, if you find the pj in the second loop, which is in the second function, if you find the point which is also not inside the current circle, now you need to find the minimum circle which includes both of these points. So so it's like one function another is calling another function. Now we find, let's call this find2, let's call find min1, let's call this find min2, which has to have these 2 points on its surface. Now the good thing is that this will not go on forever like this. The good thing is that if you at the second stage, when you say, okay, if some pk is not inside the circle, then find the minimum circle that has this pi pj pk on its surface. When you say it like this, you don't need to call another function because there's a unique circle that passed through 3 points. So this the good thing is that fortunately this doesn't go on forever. So if we look at here, so this is the same lemma. If the next pi is already inside the previous disk, we update the previous disk like this. If it's not in the previous disk, then pi has to be on the boundary of the minimum disk up to that point. All right, so this is really interesting. So if that's the heart of the algorithm, this lemma. And here, so this is the approval of the uniqueness of the smallest enclosing disk. And yeah, here is the algorithm one after another, different functions. So this is the min disk function. This is the main function above, in which we don't know which one of those points will be on the boundary. So this is the main function. We first create a random permutation of the points, and then what we do is this disk 2 is just the smallest enclosing disk containing the first 2 points. That's the unique disk in which the middle point between 1 and 2 is its center. And starting from for I 3 to n, what we do is if the next point is already inside the previous disk, then this disk is the same as the previous disk. Otherwise, we call this function min disk with points. Now this point pi, we are sure that it has to be on the disk. It's that function. And this is the minimum disk with point function. It also starts random permutation, so it calls this random permute repeatedly. I'm not sure it's needed. I mean, if we just permit the points initially at the beginning, I think it will be sufficient. Now, as you can see, this point q now which is this pi here, is now known to be on the smallest disk. Now, this point q here is special. We know that it's going to be on the disk. It has to be on the disk. Therefore, we start our disk with p1 and pq. Then from 2 to j, we do the same thing. And if we figure out that this new point pi this time here is also not on the disk, now we call a different function, minimum disk with 2 points, because we want q to be on the disk. We don't want q to be not on the disk. Q has to be on the disk. So now pi also has to be on the disk. So q and pi, both of them has to be on the disk. And therefore, we call a function with 2 points. And the good thing is that this is the last function we have, because if the new one is not on the disk, there is a unique disk that passes through q1, q2, and pi. And all the algorithms, they look very similar to each other. Now, this is a randomized algorithm. It's an incremental algorithm. And in the worst case, it may take 1 square time 2. But the good thing is that what is the probability that the ith point to be not on inside the disk that was computed in the first I-1 steps. So again, we ask the same thing. What is the probability that we go into the else statement? Imagine you have, again, a lot of points. Imagine you have 100 points. What is the probability that 101st point is the one of the 3 points that is going to define the actual minimum disk, right? Think about it like this. I mean, the first 100 points are already processed. Now, if you look at the question globally, including the 101st point, given 101 points, you have found the closest disk. The closest disk is unique, therefore it contains 3 points on it. Okay, it may contain more, but it doesn't change it actually. But what will happen is that what is the probability that one of those 3 points on the boundary is our 101st point, the last one? That's a very small probability, right? I mean, out of all those 100 points that could have determined the closest, smallest disk, the probability that the last one is that one is going to get smaller. That probability is going to get smaller and smaller and smaller at every iteration. It's the exact same thing we have faced in the previous problem. All right, so if you look at this, this is called the reverse and backward analysis. So the probability again here going to be 2 over I, and therefore and the overall complexity is also going to be linear. So the smallest disk problem, you can find the smallest disk enclosing m points in expected linear time. So just the same thing. Out of all these points, what is the probability that one of these is pi, is one of these two is pi is 2 over I? Okay, so that's the end of the slides actually. So as you can see, we have seen an incremental randomized algorithm, and we have conducted a probabilistic analysis of running time, in which we ask ourselves what is the probability that we go into the else part of this algorithm. And when we take a look at this probability and we plug that probability in our computational complexity function, we see that it takes expected linear time. The expected time of the expected running time becomes linear in this case. Okay, so this concludes our discussion on chapter 4 this week. As I said, I skipped section 4.5 and 4.6. So for the midterm, actually, I plan to have the midterm as a take-home exam, in which you're going to have like 2 days to work on the midterm exam. So it will be like an assignment, a written assignment, but with a much shorter amount of time. Instead of 2 weeks or 10 days to work on it, in that take-home midterm, you will have 2 days. All right. So I plan to have the midterm exam as a take-home in both sections. But before the exam, I'm going to also tell you which sections you're responsible from. And from this chapter 4, you're not responsible from section 4.5 and 4.6. All right, so this concludes this week. And next week we are going to, next week we are going to talk about, so let me just get this. Okay, next week we are going to talk about orthogonal range searching, in which we are going to see some index structures. KD trees, 2 index structures, KD trees and range trees. These are just basically higher dimensional index structures that allow you to make windowing queries on higher dimensional data sets. So that will be something interesting. We will see some data structures that help us do queries in sublinear time. That's next week's topic. And for next week, we are going to have both section 1 and section 2 as synchronous lectures. So I will have both Tuesday and Wednesday lectures synchronously starting from next week. All right, that's it from me today. Oh, the midterm assignment, I think I haven't announced it yet, but it will. I plan to have it after we finish. Let me take a look at here. It's on the schedule page, the tentative schedule in our course web page. It's written here. It was actually I planned first to be a synchronous exam, but then I decided not to do it like that. So I plan to give it at the end of November. So not on Tuesday, but I plan to give it on Friday, and I will have you submit it on Sunday night. All right, so you will have the weekend to work on the take-home midterm exam. So if this is week of November 30, it will be like 3rd or 4th of, so this is my calendar. Yeah, I will give it 4th of December, okay, and you will submit it by 6th of December. All right, so that's the plan. So in about 20 days from now. All right, thank you. So have a good night, everyone. That's it from me for today. See you all next week on Tuesday evening.